All right, so now we're going to look at areas in polar coordinates. So remember from the previous video, we did the graph of the sine of 2 theta, and it turned out to be a beautiful picture of a flower with 4 petals. So our graph, my marker is starting to get a little, I want to go change it for next video. Oops, I should have gone a little bit further out and then returned here. Anyways, not that important. The graph is, can you see it there? I hope so. Looks a bit dark from here. Oh well. So let's figure out how we're going to integrate. So remember that my variable of integration here, I would hope for it to be theta, okay? So what I'm going to do, remember always whenever you do whenever you're going to do an integration, you want to have a partition. So ideally, my area should be something like an integral from a to b and something that has a d theta. That would be my idea. That's what I would want it to do, because then I would get some sort of multiple of sine of 2 theta. I don't know, something that depends on it, right? So we got to figure out how to do it. So what you're going to do is you have an interval on theta. So you're going to have a partition that will depend on the angle. So a partition that is going to partition this interval, but the interval is on angles. So you're going to get a partition of angles. So for example, here, 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 and so forth and so on. You're going to partition your interval. Let's just do the first quadrant. I should have intersected there. Well, let's say that I get 0 somehow. So I'm going to partition that. And I will zoom in further because I don't think I'm going to get to explain very clearly what I need. Or I will. Let's draw this. So a way to approximate this would be by calculating the area of the sector on each one of these endpoints. So you with the area of the sector, you can then compute each one of these little areas. So what would each area look like? Well, let's say that I'm going to get a delta theta. And I'm going to make that one, it doesn't have to be uniform, but I'm going to make it uniform just for convenience sake. So that would be just the b minus a over n, and this is a partition of the angle, right? These are radians, okay? Looks very much like what we did before. So what I'm going to do now is I'm going to pick this to be the radius for the endpoint. I'm kind of doing the right endpoint, if you will. So my r sub I, the radius I'm going to pick is going to be the function. I'm assuming this is going to be r equals f of theta. So I'm going to call that function f. So in my case, my function f is going to be the sine of 2 theta. So I'm going to pick that to be f of theta I. Okay, so that's going to be my Ri. Now you got to remember here the area of a sector. And the area of a sector, what do we call it? S, I suppose, is going to be 1/2 of theta R squared. Now, if you don't remember this formula, an easy way to remember is you write it out, and if you plug in theta being 2 pi, you should get pi r squared, because that would be the area of the entire circle. And then effectively, that's what we get. All right, so this area should be written in terms of a sum that will be the sum of all these little sectors. So it's going to be the sum from n equals 1 to infinity of the theta I and then f of theta I squared. Let's write that out, and then I'm going to come up with the formula right here. So I'm going to erase this. This was just to let you know what I'm looking for. I'm going to get the formula, and then when I use it. All right, I'll erase. I'll be right back. All right, so as we had mentioned, a is going to be the limit as n goes to infinity of the sum from I equals 1 to n of the area of each one of these sectors, which is going to be 1/2 of theta I, because for each theta, I want to be doing theta 1, theta 2, theta 3 until I do my n. And then the radius, which is going to be radius squared, is going to be the function evaluated at theta I, the whole thing squared. All right, so we're going to now, the angle, however, my theta I is not quite right, because the angle that I'm opening here would not be theta, would be theta I minus theta, because theta I will go all the way down here. I just want theta I minus 1, which is actually going to be my delta theta. There's a mistake there. Let me erase it and change it up. All right, now that's better. So we have the delta theta. And now notice that as I take my limit as n goes to infinity, this is really not very complicated. It's going to end up being the integral from a to b of 1/2. This delta theta will become my d theta. And then I'm going to have just f of theta squared. So for our case, if you wanted to compute the area of the entire thing, we would do the integral from 0 to pi of the sine of 2 theta squared. Let's do 1/2 of that. Let's do the area of just one petal. So let's erase here and let's just look at the area of one petal. By the way, I should, before writing all that, I should mention that we don't need to derive this formula every time. This is going to be the formula we're going to be using. Now, if you forget your formula, now you know how you can deduce it. So, but if you remember, if you're good at remembering formulas, you just write it down. I am very terrible at remembering formulas. I have to deduce them pretty much every time I have to reteach the material because I don't remember formulas. I just like doing it. Anyway, so let's compute the area of one petal. So let's look at this. So one petal, what is the trick for this? If you wanted to do your 4 petals, as I said earlier, you would just do the integral from 0 to 2 pi, the whole circle. But now I got to figure out from where to where was the one petal drawn. So you see the graph of the one petal, if you remember our table in the previous video, we started at theta equals 0. We started here. We went out to square root of 3 over 2 as I did masterfully in that other video. No, I made a mistake. Then we went out to 1, then to square root of 3 over 2, and then returned back to 0. The angles that happened was from 0 to pi over 2. Now, if you did not draw the graph and I just asked you to compute the area of one petal, you would set your sine of 2 theta equals to 0, and you would find out that 2 theta is going to be equal to 0, pi, how am I blanking? 2 pi, 3 pi, and so forth and so on. All the integer multiples of pi, plus minus. So then you divide by 2 and you get 0 and then pi over 2. Now you don't go to pi because then that would give you the next petal. So you see, each time you get to 0, you start a new petal. And so I just need to go from 0 to pi over 2. And so my area becomes the integral, and I'm going to erase because I need space to write it. So I'm going to write it here, for example. The area is going to be 1/2 of the integral from 0 to pi over 2. And then I'm going to write the formula of the function sine of 2 theta squared. Let me erase and then we compute the integral. So we have the sine of 2 theta squared d theta. I'm going to do that circle and I'm going to do the area between these two curves. So the first question is, well, from where to where is my integral? So what I can do, what I would want to do is compute the area between the intersection points and see which function I'm actually obtaining the area of. So it's a little bit different than what we're used to. So I need to find my angles where that is going to happen. And for that, I'm going to set them equal to each other as you normally would. So 1 is equal to 1 plus cosine of theta, subtracting 1 from both sides, I get that cosine of theta has to be equal to 0. And at that point, I get that there's two values of theta. I wanted to write theta is pi over 2 and 3 pi over 2. That gives me the 2 points in the entire one revolutions of between 0 and 2 pi, where the angles, where the cosine of theta is 0. I don't know if that fit there. Hopefully it did. All right, so now I gotta be careful though, because when I start, say, at the angle 0, if I go from 0 all the way out to pi over 2, you see what I'm going to be drawing, or what I want to be integrating, is the circle, because I'm going out to the circle. Okay, so my area, I'm going to try to write it. Probably I'm going to raise a little bit here. I'm going to write here below. So my area is going to be the integral from 0 to pi over 2. That's the first intersection point. And at that point, I'm just going to be integrating the radius equal to 1. And remember, the area is always 1/2 of the radius squared. So it's going to be 1 squared d theta. So it's going to be this first part. Now, I'm going to go from pi over 2 all the way to 3 pi over 2. And I'm going to be integrating, really, the other function. Because all those angles, as I'm going out, all that radius is going to give me this. So I'm going to integrate plus the integral from pi over 2, 1/2, I keep forgetting my 1/2, from pi over 2 to 3 pi over 2. And at that point, my function that I'm going to is actually going to be 1 plus cosine of theta squared d theta. And then from pi over 2 to 2 pi, 3 pi over 2 to 2 pi, I'm going to be integrating that 1. So not very exciting, this one. I guess I'm going to do another video, because this video is already extra long. I'm going to do another video with intersection of curves. I figure that that's going to take a little bit more work, because this one is too trivial, but I just tried to come up with it on the fly. I really didn't think of anything fun. But I'll give you another video. So in the next video, I'm going to do another one with perhaps 2-3 examples of intersection of areas in polar coordinates, and do something more exciting. Well, but thank you for watching. We did a first approach to integration. We'll do another better video next time. Thank you for watching, and I'll see you in the next one.